Okay, it's working. Right. Hi guys. So today we will talk about Born-Haber cycles, and I want to dive right into this because I don't have much time. My lessons literally like start in 40 minutes or so, 50 minutes. So Born-Haber cycles. Born-Haber cycles are well, it's just a more complicated version of Hess's cycles, in which you can find either a lattice enthalpy or enthalpy change of formation, or anything else, of course, any other enthalpy that's in that cycle. But for IB chemistry, usually they would ask you to find lattice enthalpy or enthalpy change of formation, okay? And to draw out a Born-Haber cycle, which, by the way, you don't they say that you don't need to know how to do it from scratch. Yeah, so they say that they won't ask you to plot an entire Born-Haber cycle, but still you need to know how to do it. And I think it's the best way to practice is to really build the cycle from scratch, because they can ask you to fill in the arrows. Yeah, so which arrow means which enthalpy. They can ask about, for example, how you calculate certain enthalpy changes from the other known enthalpy. So they can ask anything, and if you understand how to build it from scratch, then you'll be able to solve any Born-Haber cycle task. And the key for drawing the correct Born-Haber cycle task is to really, really understand different enthalpies that are in that cycle. Yeah, and let's see. And I'm not even talking about definitions. Obviously, the word definitions you have to know, but you have to understand how to write equations for every type of enthalpy change. So for Born-Haber cycle, you need to know enthalpy change of formation, which we discussed last time. So it's when you're forming 1 mole of a compound from elements in standard state. For example, for water, it would be 1 mole of water molecules formed, yeah, in liquid state, because it's standard state for water, from elements. Which elements? The elements are hydrogen gas and oxygen gas, and and it's per 1 mole of the substance being formed, yeah. And it's very, very important to remember per 1 mole of which substance you have this enthalpy change. Yeah, that changes the whole calculation if you don't know where that one is. Okay, so formation. Per 1 mole of compound that is formed from elements in standard state, enthalpy change of formation could be exo or endothermic depending on the substance. But if they ask you to find it and don't say whether it's exo or endo, consider it exo. In most cases, it would be exo, especially in IB. Then an enthalpy change of atomization. It's always positive, and it's when 1 mole of gaseous atoms is formed from element it's in standard state. Yeah, so when you're balancing it, for example, for bromine, it would look like this. You're forming 1 mole of Br gas atoms made of elements of its element in standard state. So element bromine exists as an element as Br2 liquid. So you put 0.5 to balance it so that you have 1 in front of Br. Always positives are always endothermic because you need energy to break the bond. Then lattice enthalpy we discussed last time as well. So lattice enthalpy, it's when 1 mole of an ionic lattice is it's broken into gaseous ions. Yes, so you have 1 in front of the lattice, the compound, ionic compound, and you're forming gaseous ions. Be very careful. If you're solving older questions, they can also say that lattice enthalpy, it's the opposite reaction. Yeah, so strictly speaking, especially if you're doing A level, they say that there is lattice enthalpy of dissociation, which is this one when you break down lattice enthalpy, and lattice enthalpy of formation if you're using the opposite reaction, like the backwards. It's when you're forming 1 mole of lattice enthalpy. Obviously, the sign of enthalpy change would change, right? So if you're breaking up the lattice, which is lattice enthalpy of dissociation, that's a positive. That's endothermic reaction. If you're forming lattice, that's that's exothermic. Yes, so if you're doing the reaction backwards, Na plus NCl minus gas goes into one NaCl, that's exothermic. That's bonds forming. Well, ionic bonds forming. And again, in the like later specifications, usually they're using for IB, they're using enthalpy change of dissociation only. But especially if you're doing some school test, they can give you older questions, and there it could be the opposite reaction. Yeah, so both are lattice enthalpies, but this is lattice enthalpy of dissociation when you split the ionic lattice, and the backward reactions lattice enthalpy of formation, which would obviously be exothermic. So careful with that. For this lesson, we would only use it as a positive lattice enthalpy, so lattice enthalpy of dissociation. The next definition that you need to know, it's first ionization enthalpy, well, and second ionization enthalpy. So first ionization enthalpy, it's when 1 mole of gaseous atoms loses loses an electron to form gaseous ions. Yeah, so energy required to remove 1 mole of most loosely held electrons from 1 mole of gaseous atoms to produce 1 mole of gaseous ions, each with charge of +1. So this reaction, yeah, so basically you're removing 1 electron from a gaseous atom, and this is always positive because you're overcoming attraction between an electron and the nucleus. And electron affinity, it's kind of opposite to ionization. So it's when you're adding an electron to a gaseous atom. For example, for chlorine, it would be electron plus Cl gas goes into Cl minus gas. And this is always exothermic. Yeah, so you see most of the things with most of the enthalpy changes in the Born-Haber cycle are endothermic. Well, first electron affinity is exo. Yeah, so it's when you're adding an electron. Why is it exo? Is it exo? Because when you're adding an electron, it would be attracted to the nucleus. Yeah, so it's like, it's not the bond, obviously, yeah, but it's kind of the same as bond forming. Yes, there is an attraction between an electron and the nucleus. So you're not breaking an attraction, but attraction is formed, sort of, yeah, or just memorize it. And what's important is that second electron affinity. So if you're adding the second electron to a gaseous ion, yeah, so for example, for oxygen, what would be the first electron affinity? Well, it would be an electron plus O gas goes into O minus gas. Yeah, that's first electron affinity for oxygen atom. And then if you're trying to add the second electron, so you're taking O minus gas, what was left from the first electron affinity, and add an electron that becomes O2 minus gas, and that's positive, so that's endothermic. Why? Because an electron and negative ion of oxygen would repel, and that's why you need to overcome that attraction. Yeah, so second electron affinity, it's always endothermic. Sorry, overcome, not attraction, you overcome the repulsion. Yeah, so negative electron and negative ion repel, so you're overcoming that repulsion. Now, this is an example of a Born-Haber cycle for sodium chloride, and it would always be written in the same way, and some steps you can switch around, but in general, it's always like that. So we start off writing Born-Haber cycle by writing the solid ionic substance for which you're writing the cycle at the bottom. So I put an ACl at the bottom first. Then what I like to do is first I would write the reaction for lattice enthalpy. Yeah, so I would say that lattice enthalpy, remember the definition, lattice enthalpy, it's when you're breaking 1 mole of an ionic solid into gaseous ions. So when I split an ACl solid into Na plus gas and Cl minus gas, that's my lattice enthalpy. It's endothermic. Yeah, it's breaking ionic bonds. So it's endothermic. That's why arrow goes up. So for endothermic reactions, remember, products have higher energy than reactants. So whenever in my Born-Haber cycle the reaction is endothermic, arrow would go up. Whenever the reaction is exothermic, arrow goes down. So, and let's say we need to find lattice enthalpy. So this is the reaction that I want to find. That's my direct route. Now what I will do, now I will try to split NaCl into gaseous ions indirectly. Yeah, so I'm trying to create a route which would consist of different intermediates, but that will end up also in formation of Na plus and Cl minus gas. And that indirect route, I highly recommend to just memorize which enthalpy change, like which reactions you're doing in which order, and it would always be like that for all Born-Haber cycles with slight modifications when you have like 2 plus ion or 1 plus ion. But in general, you would use the same steps. So okay, so now let's look at this indirect route of forming Na plus and Cl minus gaseous ions from NaCl solid. So the first thing that I would do is I would write the reaction for enthalpy change of formation of NaCl. Again, essential definitions are essential. So remember, what's formation enthalpy? Formation enthalpy is when you're forming 1 mole of a compound from elements in standard state. So I'm just telling you it's exothermic. It would be written in the question. So I'm forming 1 mole of NaCl from its elements. What are the elements? Well, Na solid and Cl2 gas. Yeah. So NaS and 0.5 Cl2 gas going down because it's exothermic. So this reaction shows enthalpy change of formation of NaCl. Why 0.5? Well, 0.5 because this reaction must be balanced. Yes, so I need to form 1 mole of NaCl from elements from NaS and Cl2 gas. And to balance it out, I have to put 0.5 in front of Cl2. Arrow down because exothermic. That's the formation of an ACl. You see, now I'm a little closer to what I need. Yeah, I want to have an A plus gas, Cl minus gas, and I already split it into elements. Now the next thing that I would do is I would atomize sodium because I want to have Na gas and now have Na solid. By definition, what is atomization enthalpy? It's when 1 mole of gaseous atoms is formed from elements in standard state. So I'm taking NaS, I'm drawing arrow up because it's endothermic reaction. Yes, remember in the table, atomization always endo, so arrow up, and I'm forming Na gas. Yeah, chlorine, I haven't done anything to chlorine yet. I'm doing it one step at a time. That's why chlorine stays. I haven't touched it, so it stays the same. So arrow up, that's enthalpy change of atomization of sodium. So sodium, you see, it's even closer to what I want it to be. The only thing left to do with sodium is to remove an electron. So now I will remove one electron, well, 1 mole of electron from 1 mole of gaseous sodium atoms, and that's enthalpy change of ionization. So that's first ionization energy of sodium. I'm removing one electron, so it's electron plus Na plus gas. Chlorine, again, nothing happened to chlorine, it stays the same. Now sodium plus is in the form that I want it to be. Then I'm working with chlorine. So I need to atomize chlorine. I want to have, instead of chlorine molecules, I need to have chlorine gas, yeah? So I'm atomizing chlorine. Remember, by definition, atomization, it's when 1 mole of gaseous atoms is formed. So I'm forming 1 mole of gaseous atom from half a mole of chlorine molecules, yeah? So that's endothermic, arrow up. And then the last thing that I need to do is I need to add that electron to that atom to form Cl minus gas. And this is first electron affinity of chlorine. Remember what it was. It's when you're adding an electron to gaseous atom. And it's exothermic, yeah, because you're forming attraction between an electron and nucleus. So arrow down. First electron affinity of chlorine. And all of these would be as numbers. Yeah, these would be as numbers. And now let's see how we can calculate lattice enthalpy from these given enthalpy changes. Well, let's see. So we said that this is my direct route. Yeah, so I'm starting with an ACl and I'm getting Na plus and Cl minus gas. Right, now I will do, so I'm saying, okay, so lattice enthalpy equals to, now I'm doing the same reaction but indirectly. So if I start off with, which color should I choose? So many colors, like you can never choose. I want to choose the one that looks good on screen, but I'm not sure. Okay, so I'm starting with an ACl. I want to end with ions. Yeah, so, well, first I need to do this reaction. What is this reaction? This reaction, it's opposite to formation. You see, arrow down, it's formation. It's when you form NaCl from sodium and chlorine. I'm doing the opposite reaction. I'm doing the reaction that goes from NaCl to elements. So that's minus delta HF of NaCl. You see, because I'm opposing this arrow. And so I'm doing the reaction opposite. Oh, you can't see anything. Like this. Yeah, so I'm making a reaction that's opposite to the one that is written out. Then I need to make this reaction, which is exactly atomization, so plus atomization of sodium, right? Because I'm following the arrow, so I'm going from solid sodium to gaseous sodium. Then I'm doing this reaction, which is ionization, again following the arrow, so I'm doing exactly ionization of sodium, not the opposite. Then I'm doing atomization of chlorine, so plus. Then I'm doing where am I? Okay, there. Then I'm doing electron affinity of chlorine. Again, even though I'm going down, I'm still following the arrow, right? So because I'm forming Cl minus from Cl, that's exactly first electron affinity of chlorine. So that's why it's still plus delta H electron affinity of chlorine. Yes, so you see, I started here, made all of these reactions denoted with blue arrows, and ended with the place where I wanted to end, with ions. So that's how you find lattice enthalpy. If you needed to find formation enthalpy, you'd do the same, but this would have been your direct route, and then everything else like would have been indirect. Now I will show you another example with some other salt, some other substance. But what else I wanted to tell you here? So it's very important. So what do you have to remember? So you have to remember the order. Yeah, you can change the order of atomizations. Yeah, so for example, after atomization of sodium, you could have made atomization of chlorine and then do ionization and electron affinity. That's fine. Yeah, so some orders you can change, but obviously you cannot change lattice and you cannot change formation. Yeah, so those have to be like your first steps to make. And I recommend to just remember some order, for example, how I have written it. Yeah, so you do lattice as direct route and then formation, atomization of metal, ionization of metal, atomization of non-metal, electron affinity of a non-metal. So these you would memorize, but you'll see that there would be some modifications if you are changing the charge, for example. Yeah. But let's see, so let's do it with numbers. So use Born-Haber cycle to calculate lattice enthalpy of Kf, potassium fluoride. So the first thing that I would do is I would write potassium fluoride at the bottom as solid, yeah? So that's my Kf. Then I would write down the reaction for a lattice enthalpy. So by definition, lattice enthalpy, it's when you're breaking up 1 mole of an ionic solid to form gaseous ions. So somewhere here I would write K plus gas and F minus gas. That would be my lattice enthalpy. Lattice enthalpy of Kf. That's my direct route. That's what I will want to find. And then I would now I will build my indirect route. So I start off by writing formation enthalpy. You see it's negative. That's why arrow down. Well, not arrow down, but like the reactants would have higher energy than Kf, yeah? So by definition, formation enthalpy, it's when you're forming 1 mole of a compound from elements in standard state. So elements, what are the elements in standard state? Well, it's potassium, it's solid at standard state. A fluorine is gas, F2 gas, and it has to be balanced, so I have to put 1/2 in front of fluorine. So that's my enthalpy change of formation. Remember about halogens, yeah, so obviously they would, like in 90% of cases, they would give you binary compounds with halogens. So fluorine at standard state is F2 gas, chlorine Cl2 gas, bromine Br2 liquid, careful, iodine I2 solid. Yeah, so that you need to know. Okay, so this is formation of Kf. Now I would want to atomize potassium because I want it to be K gas. So it's endothermic, and by definition, atomization is when you form 1 mole of gaseous atoms from the element in standard state. So that would be atomization of potassium. Then fluorine I haven't changed, so I keep it as just 1/2 F2 gas. Then I would ionize potassium. So first ionization of potassium. So I'm removing 1 electron from gaseous atom. Again, endothermic, where is it? Endothermic, so arrow up. Gas plus E, and fluorine, I haven't done anything, it stays. So potassium is fine, yeah, potassium is done. I don't have to do anything to potassium. Then I need to work with fluorine, so I need to atomize fluorine. So atomizing fluorine, potassium stays. Fluorine, I'm forming 1 mole of F gas atoms, and it is balanced, right? Because I'm forming like 1/2 of F2 gas, it's 1 fluorine, and this here I have 1 fluorine. And then the last thing I need to do is I need to add an electron to fluorine gas. This is first electron affinity of fluorine, which is exothermic, so arrow down of fluorine. That's it. Yeah, so I have what I needed. Like I ended up where I wanted to end my cycle. Now I will just assign all the numbers to these enthalpy changes. I will just write them out. So I have, what do I have? I have formation of Kf, it's -563. So you see arrow down, that's the why enthalpy change is negative. Then, okay, so this one I've used. Then electron affinity of fluorine minus 348, so this arrow. Then I have ionization of potassium 418. It was here. It's plus, yeah, so arrow up. Atomization of fluorine 79. And atomization of potassium was 90, so here is 90. Right, let's check just in case. So formation negative 563, atomization potassium 90, ionization potassium 418, atomization of fluorine 79, and electron affinity 348 minus. Yeah. Okay, and then this would be my direct route. So I need to find enthalpy, lattice enthalpy of Kf. Yeah, lattice, yes. Lattice enthalpy of Kf. So that's my direct route. So I'm starting here, ending here. And I will now say that enthalpy change lattice equals to, so now indirect, what would be my indirect route? So indirectly, again, I start at Kf. So first I need to do this reaction. So it's plus 563, right? Changing, I'm doing the reaction that is opposite to formation because I'm splitting Kf into elements. So it's plus 563, yeah, arrow up. Then I'm making this one, so I'm following the arrow, so plus 90. Then this one, plus 418. What I put it here, plus 418. Then this reaction I'm making, plus 79. Then I'm making this reaction. I'm following the arrow, yeah, so I'm doing the reaction. Fluorine goes to F minus gas, and the enthalpy change for this exact reaction is minus 348, so I'm not changing the sign here. So essentially you're changing the sign only for formation enthalpy. Everything else goes without sign change. If lattice enthalpy is endothermic, yeah. Splitting the solid. Right, well that's it. And then we just have to calculate what that is. Okay, so 563 plus 90 plus 418 plus 79 minus 348. That's plus 802 kJ per mole. And of course it has to be positive, yeah, so just double check. So we're splitting up an ionic lattice, yeah, so that's an endothermic process. Okay, that's it. So that's how you do it with numbers. I hope I haven't messed up any numbers. I hope it's fine. Okay, then next, I was thinking I'll just maybe show you another example. I still have maybe like 15 minutes max. Okay, I'll just show you how to plot Born-Haber cycle without numbers, but just the cycle itself for some other substance, for example, magnesium chloride, yeah, so that you have 2 plus and 1 minus charge, and let's see what changes there. So, okay. Let's see. So let's draw out a Born-Haber cycle for magnesium chloride. Yeah, right. So I will start again by writing MgCl2 at the bottom. So this is where I start, and let's write lattice enthalpy. So lattice enthalpy goes up, and we're forming, by definition, lattice enthalpy is when 1 mole of an ionic solid is split into gaseous ions. So you're forming Mg2 plus gas and 2 Cl minus gas, right? You see why? Because magnesium is group 2, so it's 2 plus. Chloride is 1 minus, and there are 2 chlorides, yeah? So that's your lattice enthalpy. And maybe to make it a little more readable, I will try to change the colors for enthalpies. So this is lattice enthalpy of MgCl2. And then I'm making the indirect route. So first I would make formation. Formation enthalpy, it's when I form 1 mole of a compound from elements in standard state. So what are the elements? The elements are magnesium, which is solid in standard state, and the second element is chlorine, Cl2 gas. In this case, you see, you don't need any half here because it's balanced, yeah? So if you check the reaction, Mg and Cl2 goes into MgCl2, 1 magnesium, 2 chlorines, 2 chlorines, so all good. balanced. So this is delta HF of MgCl2. Next I would atomize magnesium, endothermic, so arrow up. I form Mg gas. Chlorine I haven't changed, so just Cl2 gas. This is delta H atomization of magnesium. Then I will ionize magnesium, but in this case I need to do two ionizations. I need to remove the first electron and then I need to remove the second electron. I would make it in steps. Yeah, so let's make it in steps. So first I would remove the first electron. So I'm removing the first electron and I would form Mg plus gas and E. Cl2 I haven't changed, so stays as Cl2 gas. This is first ionization energy of magnesium, yeah, because I've removed the first electron. Then I need to remove the second electron because for magnesium 1 plus charge wouldn't work. I need 2 plus charge. So again, arrow up because it's endothermic, removing the second electron. So I'm forming Mg 2 plus one more electron. So now plus 2E plus Cl2 gas. This is second ionization energy of magnesium. Sometimes in the questions they might combine these two steps into one and they would ask what is this step. Yeah, so they could, for example, go from magnesium gas directly to Mg2 plus and 2E, and then they would ask what is this? Is this the first ionization of magnesium, second ionization of magnesium, or some other stupid options? But like you have to understand that if you're combining from Mg to Mg2 plus, it's if you're making it as one arrow, then it would be ionization energy 1 plus ionization energy 2. Yeah, right. And then next, so magnesium is fine. Yeah. Then next, what do we need to do next? Next, we need to work with chlorine. So now we have to atomize chlorine. So arrow up. Magnesium, I haven't changed, so it stays. Now, what are we doing with chlorine? We are forming 2Cl gas. Why 2? Well, because we had Cl2, not half Cl2, right? So if you split into if you have a gaseous chlorine molecule, split it into atoms, you get 2Cl gas atoms. Yes, that must be balanced, and it is balanced. And since you're forming 2Cl gas, it's 2 atomizations of chlorine. Yeah, because by definition atomization of chlorine, it's when 1 mole of gaseous chlorine atoms is formed. We formed 2 moles of chlorine atoms, gaseous chlorine atoms. That's why it's 2 times atomization. And also be careful with this one. I always say be careful as if you can like die because of that. No, you just lose marks, okay? So nothing bad will happen except for you losing marks. So this is the same as bond energy for chlorine, right? Because you see what happened. You broke down 1 mole of gaseous chlorine bonds to form gaseous atoms. So it's the same as bond energy for chlorine. Right. And then the last thing that we need to do is we just need to add these 2 electrons to these 2 chlorine atoms. That's what we're doing. So where's my pencil? So exothermic, right? Remember exothermic. And it's delta H electron affinity for chlorine, but again times 2, right? Why is it times 2? Because by definition, electron affinity for chlorine, it's when 1 mole of gaseous atoms gain 1 mole of electrons to form 1 mole of gaseous ions. Yeah. So I just remind you from the table. 1 mole of gaseous atoms gain 1 mole of electrons to form negative ions. We formed 2 moles. Yeah, so we had 2 chlorine gas, 2 moles of chlorine gas, and we formed 2 Cl minus gas. So that's why it's 2 times electron affinity. So be very, very careful with all the 2's. It's like 1 mark lost very easily. But everything else is the same. Yeah, so if from this Born-Haber cycle you need to find lattice enthalpy, well, let's do that. So this would be your direct route. So lattice enthalpy equals 2, let's say. Okay, I will write it out once and then I won't have time to do plus 2 minus 2 charge, but maybe next time, or maybe you can just do it on your own. Okay, so lattice enthalpy equals 2. So I start here again with MgCl2, I end here with ions. Now indirectly, what am I doing? Indirectly, I'm doing minus formation of magnesium chloride because I'm opposing the arrow. Then I'm doing this reaction, which is atomization. Then I'm doing first ionization of magnesium. Then I'm doing this reaction, the second ionization of magnesium. Then I'm doing 2 times atomization of chlorine. Then I'm doing 2 electron affinities of chlorine. So you see same signs as before, right? Same signs as before, but somewhere you have the 2. Yeah, so 2 will be added. Okay, unfortunately, we don't have time to do MgO because I need to run for the lesson. So I will just leave it here. You can try to make MgO. So basically, the only other thing you need to practice is you need to practice MgO solid or like something else like MgS, so that the charge is +2 and -2. Yeah. So you need to practice that one. If you can try, yeah. Maybe if I have time, I will make another stream and explain this particular case. But if not, just remember that this is something that can come up in the exam. Right. So, okay, that's it. I am finishing the stream. See you next time.